Good morning. Welcome to the second class of the module 3 of digital electronics and microprocessor. Okay. So at this point of time, first to begin with, let's quickly have the recap of what we had seen yesterday. Right. It all started with the introduction part of the basic definitions like what is a microprocessor. We stated it is a programmable device that takes in input and performs some arithmetic and logical operations over it and produces a desired output. Okay. So in other words, you use the right words something like fetch, decode, and execute. So those are the three words which we expect mostly in the times of the definitions of microprocessor, right? So in other words, we defined microprocessor as a digital device on chip which can fetch instruction from memory or from any device, decode in the sense perform some operations on it, and execute them and give the results. So that was what the definition that we have seen. Then we had seen what are the different processors which are available, right? Terms which are used in microprocessor, right? The terms like instruction set, which is nothing but a set of instructions that a microprocessor can understand, right? And something term which is called bandwidth, which states the number of bits processed in a single instruction, right? Then the third was a clock speed that we had seen, right? Clock speed, the one that determines the number of operations per second, right? Something like the processor can perform, okay? And which is usually represented in terms of megahertz and gigahertz, right? So that is the third one, the third term. Fourth term was word length, right? Which depends on the width of the internal data bus register ALU. Okay, as we have 8085 processor, which is an 8-bit processor, it can process 8-bit data at a time. Okay, so that's with respect to the word length. And on the last term that we have seen was the data type, the types of data which my microprocessor can understand. Something like a binary or BCD or ASCII or signed and unsigned numbers, right? So those were the terms that we had seen yesterday in our class. Then we went into the features of microprocessor, something like the cost effectiveness, size, the amount of power consumption. Yes, microprocessor 8085 is a low power consumption device just because of it's been manufactured by MOS technology, metal oxide semiconductor technology. Yes, that technology uses low power consumption. So that's the reason behind our 8085 is also a low power consumption device. Right, then we had seen two of the other features like versatility and reliability, right? Versatility is nothing but the usage of the same chip for n number of applications, right? We'll say, for example, you are using for one typical application and gradually if that process is over, then you just want to move on to another application. No problem. Use the same chip, reprogram it and use it, right? So that's what is versatility is all about. Then it is the last feature was the reliability, which is something like the failure rate, right? The IC lifetime, the failure rate of the IC of microprocessor is very low, right? So that's the reason behind we call this as one of the most reliable feature of that, right? So most important is the low power consumption, versatility, and the reliability. Okay, so those are the features of your microprocessor, right? Then later we moved on to the types of processor which we have seen as CISC, RISC, and special process. When we say it is a RISC, it was reduced instruction set computer. CASC is for complex instruction set computer. Yes, so those were the two processes which are broadly available, right? When we say it is reduced instruction set computer, this is mainly designed to reduce the execution time of the system, right? How this execution time is reduced is by simplifying the instruction set in the computer, right? And here, one of the advantages that it works on one clock cycle, right? Each instruction requires only one clock cycle to execute results, right? Thereby, this reduces the efficiency as there are more number of codes, right? And since there are more number of codes are there, you will have to go for more number of RAM size. So that's a drawback in that. Okay, and a few of the RISC processes which we can say is as HP 7100 is one of the RISC processor, right? And then we have got TS RISC processor, okay? And those were the RISC one. And CISC is complex instruction set computers. And this complex instruction set computer is mainly designed to minimize the number of instructions per program, right? Here we are ignoring the number of cycles per instruction. There we were using one cycle per instruction. Here the number of cycles is not being considered into as a major factor, right? As a result of which, what is the thing is the RAM size is getting low comparatively. And few of these CISC processors are Intel 80486, right, which is i4, then IBM 370, all these things falls under the CISC processor. Okay. Then we had seen some special processors like coprocessor, which can handle only a particular function for a number of times. You use subroutine in your programs, right? The program which you want to use a number of times repeatedly. So similar way, a processor need not have to work on all the operations at times. So some operations which are at regular usage, that can be assigned to a coprocessor. Okay, thereby the main processor timing and the clock cycle could be saved. Okay, some of the co-processors or 8087 that we use, which is a math processor which we use with 8086, right? And then we had seen something like an input-output processor, which is again a special processor. Okay, so this input-output processors are those which are specially designed for handling your input and output devices, like something like a keyboard or a mouse or a graphics card or a direct memory access, access your memory. So these are your specialized process based on the applications of input-output. Okay, then the third one was transputer, and the fourth one was DSP, right? Transputer, its expansion is transistor computer, right? So this is a specialized design processor with its own local memory it has got, right? And this is mainly used to link one with the other, okay, for inter-processor communications. Okay. And last one is a DSP, a digital signal processor, right? So as the name implies, it needs digital. It works on only on the digital signal. So you need to have, if your input is an analog, then you need to have an analog to digital converter and convert your input into a way in which your processor can understand, right? And ultimately, your processor is going to give an output in terms of digital, right? So at that point of time, you need to have a converter of digital into analog. If your end final element, which is going to work on the field, if it accepts only analog signal, then you will have to convert that. So in DSP, you need to have two converters. One is analog to digital converter, and the other one is digital to analog converter for the better operation. Okay, so these were the few process that we had seen, right? And then we had gone on to the evolution of microprocessor. We had seen the evolution with starting from 8080, right? 8080 was the first microprocessor chip that was introduced, and that was in the year 1974. Okay, which used only 6,000 transistors with a bandwidth of 8 bits per second, 8 bits and a clock speed of 2 megahertz. Okay, after that came is 8085 in 76, which is also an 8-bit processor, 8-bit data, and with a clock speed of 5 megahertz. The more the clock speed, the more the execution time, lesser the execution time is. Okay, and after 8085, it was 8086, right, in 78. And gradually it went on till P4 in 2000, and then you have your P10 and other cases. Okay, so that is all the evolution of microprocessor that we had seen, and then we moved on to the architecture of 8085. Okay, so under the architecture we had seen something like what is the basic configuration that it was following, right? It is an 8-bit data bus. Our 8085 is 8-bit data bus, 16-bit address bus, and 16-bit program counter and 16-bit stack pointer, right? And it has got some registers, individual registers, B, C, D, E, H, L, flag registers, accumulators. This 8085 requires only plus 5 volt supply, and it operates on a clock speed of 3.2 megahertz, single clock. Okay. So this is what we had seen about the configuration part. Then we moved on to the architecture, in which we had seen a few of the functional units which were available. Okay, and we went one after the other. Okay, so that is what we had seen yesterday. Okay, so is there any part which you need to have which you say that it is not clear or which is not understandable, then you can let us know now before we proceed on to this class. Okay, so just wait for a minute. If there is at any point any part of what was covered yesterday was not clear, or you want us to repeat it today, you can just let us know now. Right? Take a minute or a few seconds, drop a message in the chat box or unmute yourself and let us know. We'll wait for a few seconds. If there is no response, that means that it is understood, so that I will proceed further. Okay. Since there is no response in the chat box, that means it is clear, so that we can proceed on to today's class. Okay, taken for granted, right? Okay, getting into the point of today, we are going to see about the pin configurations of that 8085 processor. Okay, so as you can see on the screen, your 8086, 8085 microprocessor, it has got 40 number of pins, right? And it's on the left side, it starts with your X1, X2, reset out. Okay, so this is you on this left side, you have got 20 pins, on the right side, you have got 20 pins, right? So how is that this 40 pins are being categorized is, if you can clearly look at the screen, you will find that there are address bus and data bus. All those pins which are coming with the representation of A0, A1, A2, A3 or something like address bus, which are 16 in numbers, A0 to A15. Okay, so in that you will be able to see, I hope you are able to see that from pin number 12 to 19, you have got your AD 0 to AD7, right? Which is nothing but A0 to A7 is mixed with the 8 data pins of D0 to D7, right? So that's why it has been available in terms of AD0 to AD7. Then your AD8 to AD15, which is from pin number 21 to pin number 28, right? So those are your address bus, right? And this address bus are unidirectional. Okay, that is a bit flow from one direction from the processor unit to the peripheral devices. Okay, and then you have got another pin by name ALE, right? Can you find out where that pin is? ALE, which is in pin number 30, which stands for address latch enable, right? And the purpose of that pin is it will go to high during the first T state of a machine cycle, and if its value is 1, otherwise the data bus is activated, right? To make sure whether it is going to work on address bus or data bus, it is in this pin state is what is determined, right? If its value is 1, you will be working on the address bus, or otherwise it will be working on the data bus. Okay, then you have got a pin of IO/M bar, right, which is in pin number 34. Are you able to see that? Pin number 34, IO/M, which stands for your input, output, or memory. Okay, so this is a status signal which determines whether the address is for the input, output, or for the memory. Okay, when we give an address, or when we want some data from an address, or when we want put some data into the address, into the memory or IO devices, we will use this pin only, right? When this pin is set to high or at logic 1, okay, the address in the address bus is for the IO device. As you can see that IO doesn't have a bar on the top, right? Okay, so that means when this pin is with 1, a logic high, right? That means this pin is going to make sure that the data which is available is moving to the addresses on the address bus is for the IO devices. And when this is 0, right, the address in the address bus is for the memory. Okay. And then you find two pins, S0 and S1. Can you identify where that pins are? S0 and S1. S0 is in pin number 29 and S1 is at pin number 33. Am I right? Are you able to see that, right? I hope you are able to see. S0 is at 29 and S1 is at 33, right? So this pin or the status pins, this looks at the different operations along with the IO devices, right? If S0 and S1 are at logic 1 and if your IO is on logic low, right, then what your data bus does is it goes and fetches the opcode. Okay, opcode is nothing but a command given to the processor. Okay, and if this S0 is equal to 0 and S1 is equal to 1 and if IO bar M is equal to 0, then memory read is the operation that is going to do. Okay, when we say IO slash M is 0, it means all the operations are done in memory. When we say IO slash M is equal to 1, then it is done on the IO, input output. Okay, so that is what is the speciality of this 4 pins, 3 pins, S0, S1, IO slash M bar. Okay, then you have got a pin RD bar and WR bar. RD bar and WR bar. At pin number 32 is your RD bar, pin number 31 is your WR bar. RD bar stands for read operation and WR stands for the write operation. Okay, when this is low, then the selected memory or the IO device is on the read operation. Okay, and when our write bar is pin is low, the data on the data bus is on either on the memory or in the IO location. Okay, so you are just trying to find out where your data is going to be, whether it is going to do a read operation or the write operation. It's purely based on the signal that is available at that pin, right? And then you will find a pin called ready, right? Ready is at number 35, right? So this pin, it senses whether the peripheral is ready to transfer our data. When we say peripheral, it is the other device, external devices that is available, which is connected to your processor, right? Might be a keyboard or might be a memory or might be a display. Anything can be called as a peripheral, right? So this senses whether the device is ready for transfer of data or not. Okay, that means when this ready pin is at high, right? That means that the peripheral is ready. It indicates that the peripheral which is connected to it is ready for data transfer. And if it is at low, that means it's otherwise. The microprocessor waits till this pin has to go high for that to have a data transfer. Okay, so that's the purpose of this ready pin. Okay, then you have got a few pins like VCC. VCC stands for VCC is at pin number 40, which is a power supply 5 volt, right? And at pin number 20, you have got your ground. Okay, and you have got your X1 and X2 at pin number 1 and 2, which is an external crystal oscillator for giving the desired frequency, right? Clock frequency of 3 megahertz to the system is required, right? 3 to 6 megahertz can be done with the crystal oscillator, quartz crystal. So that is made out there, right? And what else is there? Okay, here you will find a few things like INTR, which is an interrupt pin. INTA at pin number 11 is interrupt acknowledge pin, and RST 5.5, 6.5, 7.5, and trap. These are the different interrupt signals which are available there, right? And your pin number 4 and 5 are SOD and SID. This is serial out data. This is serial in data. Okay. And hold and hold acknowledge are for the DMA purpose, right? This hold and hold acknowledge DMA signals, that means direct memory access signals. Okay, so this hold, if you see the first one, hold at pin number 39, right? This indicates that another device is requesting the use of the address and data bus. Okay. So whenever there is a request from other device for use of this processor, it sends a hold signal. At times, what happens is when your processor gets a hold request, the microprocessor which is working on all the data bus and the address bus, that completes the current work of it, and then hands over the address bus and the data bus to the device which really needs the uh, operation, which needs a processor. Okay. So after that is done, then that will be acknowledged by a signal called hold acknowledge. Okay. When the hold acknowledge is given, that means the processor can take back the data bus and the address bus for its own purpose. Okay, from the peripheral device. So that's the description of your hold and hold acknowledge. Okay, and then you have got a pin like reset out and reset in bar. Okay, so this reset out is a pin number 3, reset bar is a pin number 36. This reset out, what it does is this indicates that the processor is being reset. Okay, and this pin can also be used to reset the other devices which is connected to it. You can also reset the peripheral devices connected to the particular processor using this pin of reset out. Okay, and then you have got a pin called reset in bar, right? So the signal which is available here, if it is at logic 0, then what happens is the program counter will be set to 0. Okay, and the microprocessor unit on the whole will be reset. When this happens is, remember this, when the signal to this pin is logic low, this is what that happens. Program counter will be set to 0 and the microprocessor unit will be reset, right? So this is how your 40 pins available in your 8085 is all about, right? So whatever the uh, architecture what you have seen, right? In the architecture, you might have seen the different pins available from the timing and control unit, your interrupt, your SID, SOD, serial data, and your memory registers. All those pins are now connected in this fashion in the 8085 IC. Okay, so this is what is to do with your um, pin configuration. If you want, you can just make a copy of it and let me know if I can proceed further. Okay. You give you a few minutes. Do copy and here, as far as the evaluation point of view, we will have a primary look at. It's quite easy to represent. When you look at this pin diagram on the whole, first two things, make sure that it is for the crystal oscillator. Okay, and when you come to the pin number 20, it is for ground, and pin number 40 is for the supply voltage. Finish off these 4 pins first of all, right? And then from pin number 12 to 19, AD0 to AD7, pin number 12 to 19. Then go on to the other side, pin number 21 to 28, A8 to A15. Okay, then after above this pin number 12, go on for the interrupt pins. INTA bar, INTR, reset sound 5.5, 6.5, 7.5, trap. Then you have got SID, SOD, reset out. Here below VCC, it is for DMA, hold and hold acknowledge. Then you will have a clock out. This is the area where we might have to be very clear at, right? So it's quite easy to remember, but it needs some look at again and again. Okay. If you have done copying, making a note of it, let me know through a message in the chat box. We'll wait for a few minutes, and then even if there is no message, means it is understood. I hope I am audible, and at the same time the screen is also visible to you. Students, yeah, okay. Yeah. Sedu, thank you. Praveen, thank you. Any responses from A and B? Yeah, that's what I'm looking at. A and B. A and B response is only for Madam, I suppose. Yeah. Ritesh Nagaraj, thank you. Thank you, Ritesh. You are at my side. Indian Constitution is working a lot, I suppose. Okay, good. Shall we proceed to the next one? Yeah, Praveen, Sedu, Saranya. Yeah, thank you. Premja is on this side. Thank you. Pratish Nagaraj, Sudarshan. Yeah, thank you. Thank you. Okay, then we'll move on to the next part of it, right? So, till now we have seen about the architecture and the pin configuration, right? So, the next part that we are going to see is on the addressing modes of 8085. Okay. So this addressing modes of 8085 are five in numbers. Five modes of addressing are available in 8085. Okay. So what are they are something like first one is immediate addressing mode. Second one is register addressing mode. Third one is direct addressing mode. Fourth is indirect addressing mode. And the fifth one is implied addressing mode. Okay. So note down first one is immediate. Second one is register. Third one is direct. Fourth one is indirect. And the fifth one is implied. So these are the five addressing modes which are available in our 8085 processor. Okay. So looking at what this each and every addressing mode does is, well, let's first look at the first addressing mode, immediate addressing mode. Okay. So in this mode, it's either the 8-bit or the 16-bit data. Okay. You might be looking at why is this 8-bit or 16-bit data? Okay. It depends on, right? If it is on the operation side, you will have to look at, right? If your processor requires an 8-bit data, then it is 8, or if it is that, then with 16 it is that, right? So what happens is here, whatever the data that you just want to key in or to give your process to your processor, you give that directly to a register. Okay, when you give the data value directly to the register, then it is something like this, right? So the, for example, there is a command like MVI, which stands for move immediate. When we look into the instruction set of the upcoming time, upcoming sessions, you will be able to find instruction sets where we will understand what is this MVI, MOV, LDB, and all about, right? So this MVI, first of all, it stands for move immediate. There is a term called immediate which is available. So the instruction something goes like this: MVI k comma 20, right? That means this 20, the data, will be copied to the K register. Okay. Now there might be a question. Is there a question? First of all, let me keep that window open. Is there any question? Looking at that command. Looking at the command MVI k comma 20. No question. Let me break the silence. Okay. So here, MVI k comma 20. What happens is, I said the data 20 is moved to the K register, right? But in the architecture, if you look at, there is no register. It's called K register, right? There might be a question. That should be a question, right? Think for an answer for that and come out with an answer. Why is this person has given an instruction called K comma 20? Right? Since you didn't ask me a question, now I'm posing that question to you. Okay, just try to get me an answer for that. Right? So whatever the data that you are giving, it immediately moves on to that particular register value. Okay, so such things are called, such modes of addressing is called as immediate addressing mode. Then you have got something called the register addressing mode, right? It is between the registers. Okay, copied from one register to another register. Look at the example MOV K comma B. K is a register, B is a register. Whatever the data which is available in the B register is now moved to the MOV stands for move operation, right? It's moved to the K register between registers. That is your addressing mode of register addressing mode. Okay. Now, direct addressing mode is the data is directly, it will be copied from the address to the register. Earlier in immediate addressing mode, we had seen data is moved to the register. Here in direct addressing mode, here an address is specified. LDB stands for load B register. Okay. So what this does is the data which is available at the memory location K 5000 is now moved on to the B register. Am I making the difference clear? Earlier in immediate addressing mode, it is the data is 20 and it is moved directly to K register. Here in direct addressing mode, the data is available in a register address. The register address is 5000. It's an example, right? 5000 is a register address. So in that register address, there is some data which is available. So now that data will be moved on to the B register. So this is a mode of transfer of direct addressing mode. Okay. Now getting into the next addressing mode, which speaks about indirect addressing mode. Okay. So under indirect addressing mode, by using the address pointer to the registers, there in direct addressing mode, from a register it moved to the, from an address it moved to the register. Okay. Now if you look at an example here, move K comma B. Okay. Which means that the data is transferred from a memory address pointed out by the register to the K. Here that B register is not having a data. It is having an address specified. That address will have a data. Hope I am able to make this point clear. Earlier direct addressing mode, their address was directly specified, which we had the data. Now in indirect addressing mode, it is a data move K comma B. In this B register, there is an address which is mentioned. That address will hold the data, right? And from there, the data is now pushed to the K register. So that's where the difference of direct and indirect addressing mode lies. Okay. And the last type of addressing mode is implied addressing mode. Okay. The implied addressing mode is something like there is no data or there is no registers which will be available there, right? It will be a simple command which does an operation on the previous instruction. Okay. For example, CMP. CMP is an instruction which is used for comparing or complement. Okay. So under that case, it does only with the accumulator part, which is what is stored in the accumulator. Okay. So that is implied addressing mode. Is the 5 types of addressing modes clear? Let me repeat it once again. It is immediate addressing mode, register addressing mode, direct addressing mode, indirect addressing mode, and implied addressing mode. Is the addressing modes of 8085 clear? Silence indicates clear or unclear. Once again, explain all of it, sir. Oh my God, who's that? I just, oh, just a minute. Yeah, Praveen. Praveen, just look on the screen. Immediate addressing mode பொறுத்த வரைக்கும், can we go in the language, Tamil? Okay. Just for the sake of understanding, for a few minutes, right? Immediate addressing mode பொறுத்த வரைக்கும் என்ன பண்ண போறோம் அப்படின்னா, அந்த டேட்டா வேல்யூவை டைரக்டா கொண்டு போய் ரெஜிஸ்டருக்குள்ள உட்கார வச்சிருவோம். ஓகே. 20 அப்படிங்கிறது வந்து இட் இஸ் a data value. So that data value அப்படியே கொண்டு போய் இமீடியட்டா அந்த கேங்கிற அந்த ரெஜிஸ்டருக்குள்ள கொண்டு போய் உட்கார வச்சிட்டோம். அப்படி வச்சோம்னா அந்த மோட் ஆஃப் ஆபரேஷன் வந்து இட் இஸ் இமீடியட் அட்ரஸிங் மோட், right? அடுத்தது பாத்தீங்கன்னா register addressing mode, right? In the register addressing mode பொறுத்த வரைக்கும் you will move something like move k, b அப்படின்னு கொடுத்தனா the data in the b register is copied to the k register. Okay, b registerல என்ன டேட்டா உட்கார வச்சிருக்கேன், say for example அந்த 20 அப்படின்னு நம்ம ஃபர்ஸ்ட் எக்ஸாம்பிள்ல கொடுத்த அந்த 20 அப்படிங்கிற வேல்யூவை b ரெஜிஸ்டர்ல ஸ்டோர் பண்ணி வச்சிருந்தேன் அப்படின்னா இந்த இன்ஸ்ட்ரக்ஷன் move k, b அப்படின்னு கொடுக்கும்போது அந்த 20 அப்படிங்கிற டேட்டா which is available in my b register will now move to the k register. Okay, that is the second addressing mode. இது வரைக்கும் clear? Is that okay, Praveen? These two addressing modes. Immediate பொறுத்த வரைக்கும் டைரக்டா அந்த டேட்டா உட்கார வைக்கிறோம். ரெஜிஸ்டர் அட்ரஸிங் மோட பொறுத்த வரைக்கும் அந்த டேட்டா எந்த ரெஜிஸ்டர்ல உட்கார்ந்திருக்கோ அந்த ரெஜிஸ்டர்ல இருந்து இன்னொரு ரெஜிஸ்டர்ல we are going to make it sit, right? So that's the first two cases. Third case is my direct addressing mode. இந்த டைரக்ட் அட்ரஸிங் மோட்ல என்ன பண்ண போறோம் அப்படின்னா ஒரு அட்ரஸ் ஒன்னு ஸ்பெசிஃபை பண்ணுவேன். இப்போ இங்க கொடுத்திருக்கிறதுல பாத்தீங்கன்னா 5000 அப்படிங்கிறது it is an address which I am going to mention. So that address will hold some data. அந்த 5000 அப்படிங்கிற அட்ரஸ்க்குள்ள ஏதோ ஒரு டேட்டா உட்கார்ந்திருக்கும், right? So when I use this direct addressing mode, the data which is available in the address 5000 will be moved to the b register. ஏன்னா அங்க LDB ன்னு கொடுத்திருக்கிறேன். LD stands for load, B stands for b register. Okay, so this is my direct addressing mode. Indirect addressing modeல என்ன வித்தியாசம் வரும் அப்படின்னா அந்த b ரெஜிஸ்டருக்குள்ள நான் வந்து ஒரு அட்ரஸ் வேல்யூவை உட்கார வச்சிருக்கிறேன், ரைட்? அந்த அட்ரஸ் வேல்யூல என்ன டேட்டா இருக்கோ அந்த டேட்டா will be moved to the k register. ஸோ ஒரு ரெண்டு கமாண்ட் ஒரு இந்த இன்ஸ்ட்ரக்ஷன் பாத்தீங்கன்னா move k, b அப்படிங்கிறது இன்டைரக்ட் அட்ரஸிங் மோட்லையும் கொடுத்திருக்கிறேன், ரெஜிஸ்டர் அட்ரஸிங் மோட்லையும் கொடுத்திருக்கிறேன். Hope you are able to see that same command I have given for both register addressing mode and indirect addressing mode. But the difference what I am saying is in the register addressing mode that b register had some value that is moved to k register. But in indirect addressing mode, b register is not having a data. It is having an address which has a data. So now that is the difference between that and this. Okay. So last implied addressing modeங்கிறது இதுக்கு வந்து நமக்கு எந்த ஒரு ரெஜிஸ்டர் சம்பந்தமான ஆப்பரன்ஸ் எதுவும் தேவைப்படாது. ஆப்பரன்ஸ் அப்படிங்கிறது அந்த k, b ஆர் 5000 இந்த மாதிரி கொடுக்கக்கூடியதெல்லாம். ஓகே, என்ன பண்ணணும் அப்படிங்கிறது நம்ம கொடுக்கக்கூடிய அந்த கமாண்ட்லயே இருக்கும், cmp, cp. ஓகே, ஸோ அந்த மாதிரி இருக்கக்கூடிய அட்ரஸிங் மோட் எல்லாமே வந்து இட் இஸ் ஆல் அபவுட் இம்ப்ளாய்ட் அட்ரஸிங் மோட். இஸ் தட் கிளியர்? இஸ் த டிஃபரன்ஸ் இஸ் கிளியர்? Let me know. Sedu says clear. Thank you. Somebody from A and B. Is addressing mode clear? Pratish, thank you. Yeah. Okay, now getting into the next part, we are going to speak about the interrupts. Of course, in your curriculum and syllabus, if you see interrupt comes after your instruction set. Okay, but let us first finish off this interrupt and then we will move on to the instruction set. Okay, so interrupts பொறுத்த வரைக்கும் we need to understand what is an interrupt is all about, right? So these interrupts are nothing but a signal which is generated by an external device. For what? To request the processor to perform a task. Okay, say for example a keyboard connected to a processor will give an interrupt, right? How it gives an interrupt? Whenever you are pressing a key on the keyboard, that will any alphabets or the numericals which is being pressed on the keyboard, the signal will be sent to the processor saying that there is a key which is pressed in the keyboard. So this process of communicating a device which to your processor is called as an interrupt. Okay, so that is interrupt, and here we have got some 5 types of interrupts. 5 interrupt signals are available, right? Which are trap, RST 7.5, RST 6.5, RST 5.5, and INTR. Okay, so these are the 5 interrupt signals which are available. Okay, And these interrupts are classified as uh, vector and non-vector, okay, maskable and non-maskable, hardware and software. Okay, so these are the classifications of your interrupts. Just copy down what is on the slide for a while, and then we'll move on to the explanation of the types of interrupts. Okay. And one more thing you should remember, when I say 5 interrupt signals are available, right? Trap, RST 7.5, 6.5, 5.5, INTR. Remember this in the same order, right? Why I say you is, there might be a question, which is the interrupt which has got the highest priority? The first one that we have represented, TRAB, trap. That is the interrupt that holds the highest priority, which is followed by RST 7.5, followed by 6.5, then 5.5. And least priority is given to INTR. That is the order of priority that it is given. Okay. So copy down what is an interrupt, copy down the list of interrupt signals, then copy down what are the classifications. Yeah, hope you have copied. Now let us get into, yeah, thank you, Vikesh. Now let's get into the understanding of what are the different classification of interrupts, right? When you look at the first one, vector interrupt, right? So vector interrupt is nothing but the interrupts, out of the 5 interrupts, one is a non-vectored interrupt and the other 4 are the vectored interrupt. Which, how do I say that is, the address is specified for those 4 interrupts like trap, 5.5, 6.5 and 7.5, right? So the address, whenever an interrupt comes through this 4 pin, the processor will understand that this is an interrupt. So from this pin, so I can just directly get into that particular address and find out what is the data which is available there. Or what is that I have to do. So that's how your processor understands, right? So that is whenever you have an address, it is a vectored one. Okay. Second one is a non-vector interrupt, something like INTR. Here the interrupt address is not known to the processor. Okay. So what happens is the address has to be sent by a device to perform the interrupts. Like whenever you connect some peripheral devices to it, so those peripheral devices falls onto this signals coming from the peripheral devices will be done on this non-vector interrupt, which is through INTR. Okay, address is known address, then it is vector. It is unknown address, then it is non-vector. Then there is something called maskable interrupt and non-maskable interrupt. Okay, so here maskable and non-maskable is, from the word it is clear, right? I can enable and disable some interrupts, right? Out of the five, we have got sectored four as vector, one as non-vector. So we'll now have to take up the vector input only. Only those address available interrupts only can be either enabled or disabled. Okay. So out of those four which are available, RST 5.5, 6.5, 7.5 and trap, those RST 5.5, 6.5, 7.5, they can disable the interrupt by, they can be disabled by writing some instructions on the program, right? You can, it can, they can be enabled also. While the trap is an interrupt which cannot be done, which cannot be disabled, which will be enabled at all times only. Okay. So first was address away known, address not known. Second is interrupts which can be disabled, interrupts which cannot be disabled. Okay. So that's where the first four classification of interrupts is. Then on the fifth and sixth, we have software interrupt and hardware interrupt. Okay. The interrupts that we had set in the 8085, trap, RST 7.5, 5.5, 6.5 and INTR, those are your hardware interrupts. That is the interrupts which are coming through the pins of your 8085. When you look at your 8085 pin, you will find that, right? Trap, RST 7.5, 6.5, 5.5 and INTR. So there is a specific hardware assignment which is done here through the pin. So they are your hardware interrupts, right? Like how I have a hardware interrupt, I can also do some software interrupts which are available through my programs. They are nothing but RST 0, 1, 2, 3, 4, 5, 6 and 7. Right? So here in this type of interrupt, what you do is, as a programmer, you add a few instructions to the program and try to execute that as an interrupt. You can give a memory location, and that memory location will give a signal as something like an interrupt. For example, at a memory location, I can devise a small program, a delay program, right? Which means after 3 seconds, I should do this operation. Then what your processor does is, for 3 seconds there will be something which is happening at either RST 0 to 7. After 3 seconds, either of from those point of software interrupts, I will get a signal to the processor that 3 seconds is over. But how is that 3 seconds is being defined? It is did by myself as a programmer, as through a program, right? So that is how you can do some specific programs on your device, and you can use that also as an interrupt. Okay. So that those are eight numbers which are available. RST 0 to RST 7. Is the classification of interrupts clear? Vector, address known. Non-vector, address is not known. Maskable, anything, any interrupts which can be disabled or maskable. Okay. Non-maskable, trap is a non-maskable because it cannot be disabled. Software interrupts, RST 0 to RST 7, which is a programmed by a programmer for as an interrupt instruction, right? And the hardware interrupts are the basic 5 interrupts which are hardware connected through the pins of 8085. Is that okay? Is that okay? Thank you, Sedu. Praveen, yeah. Okay. From A and B. Yeah, Ratish. From A section. From section A. Is anybody available in section A? Yeah, Arunita, thank you for representing your class, right? Okay, right. Hope I can, I'll take it for granted that you understood and it is clear to you, right? Moving on to the interrupts, right? 5 interrupts that we have seen. And very important thing, there is a terminology called ISR, which stands for Interrupt Service Routine. Okay. Whenever we speak about this interrupts, along with that 5 hardware interrupts that we have, we also should understand this terminology of ISR. Okay, interrupt service routine, which is nothing but a small program. Okay, that when executed, services the corresponding interrupting source. Okay. So it's a program something like whenever there is an interrupt which is available at RST 7.5, give priority or do this operation with the data. Something a program like that is what is ISR is all about, right? So there might be a 2 marks definition which is asking for the necessity for ISR. Okay, which is nothing but a small program or a routine that when executed services the corresponding interrupting source. Servicing அப்படிங்கும்போது இட் இஸ் இன்னும் சிம்பிளா சொல்லணும் அப்படின்னா ஒரு 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 டிவைஸ் வந்து இன்டரப்டா வரப்போகுது அப்படின்னா சர்வீசிங் அப்படின்னு ப்ராசஸர் எதை சொல்லுவோம் அப்படின்னா அட்ரஸ் பஸ்ஸையும் டேட்டா பஸ்ஸையும் அந்த இன்டரப்ட் கிட்ட ஹேண்ட் ஓவர் பண்றது தான் சர்வீசிங். ஓகே, அந்த ரெண்டுத்தையும் நம்ம கொடுக்கும்போது என்ன ஆகும்னா அட்ரஸ் பஸ் ஸ்பெசிஃபிக்காக மென்ஷன் பண்ணி டேட்டாவை கொண்டு வந்து அந்த இடத்துல உட்கார வச்சு. ஓகே, ஸோ தட் இஸ் த ISR இஸ் ஆல் அபவுட். Then it is based on the priority. We have listed down the 5 interrupts, right? So either you can copy down on the whole or trap அப்படின்னு இருக்குல்ல அந்த 5 இன்ஸ்ட்ரக்ஷன்ஸ் போட்டிருக்கோம்ல trap RST 7.5 6.5 5.5 and INTR அது பக்கத்துலேயே ஒரு ஹைஃபன் போட்டு mention this address. Trap போட்டு ஹைஃபன் போட்டு 0024. Okay, this 0024, 003C, 0034, okay, and 002C are the address which are specified for this interrupts location. Whenever such interrupts are coming, that interrupts will transfer the control to this particular location. Okay, whenever there is a interrupt which is coming from here, so at that point of time the transfers the interrupt will transfer the control to this memory location. Trap la irundhu vandaduna indha memory location ku poidum, and the day and the interrupt மூலமா வரக்கூடிய data இந்த location குள்ள தான் வந்து உட்கார்ந்திருக்கும். Is that clear? Okay, so now moving on to this trap. Trap is maskable non maskable அப்படினு பார்த்தோம்னா trap is a non maskable interrupt. Other 3 are maskable interrupt. So whenever you are writing about this, first point is mention whether it is non-maskable or maskable. Then you speak about the priority part of it. As we said, trap is with highest priority. This is second highest, third highest, fourth highest. This is the lowest. So if you look at here, highest priority among all the interrupts, second highest priority, third highest priority, this is fourth, and this is the lowest. So even if you forget what to write, 3 points that we always look at on this particular thing, whether it is maskable or non-maskable. Point number 1. Second one is what is address location which is given to it. Third one, what is the priority level of it. So these 3 things, if you can keep it clear, then you can easily proceed with this expected definitions. Okay. So here by default, this is, if it is enabled, it is enabled until it gets acknowledged, right? In case of failure enna agum appadina ISR la enna irukko adu appadi execute agum. It executes as ISR and sends the data to the backup memory. Inge backup memory appdi nama sollakudiyadhu vandu indha memory dhaan. Okay, adhe mari RST 7.5 ku it is again a maskable interrupt, second highest priority. When this interrupt is executed, the processor saves the content of the PC register. PC register அப்படிங்கிறது program counter register into the stack and branches to this memory location address. Okay, then it is 6.5, 5.5. It is the same case. Always, whenever that interrupt is coming, that will be executed. Processor saves the content to program counter, stack branches to this address. Processor saves the content to the of the program counter register into the stack and branches that to this address. Okay. And the last one, if you see INTR, INTR is nothing but a maskable interrupt, and this has got the least priority among all interrupt, and it can be disabled by resetting the processor. Resetting the processor அப்படின்னா the reset அப்படின்னு ஒரு பின் இருந்தது இல்ல, அந்த பின் எப்பெல்லாம் நம்ம ப்ரெஸ் பண்றோமோ, எப்பெல்லாம் நம்ம மைக்ரோ ப்ராசஸர் வந்து ரீசெட் ஆகுதோ அப்ப எல்லாம் இந்த INTR அப்படிங்கிற இன்டரப்ட் அப்படிங்கிற அந்த பின்னும் வந்து ரீசெட் ஆயிடும். Okay, so this is all to do with your interrupts. Again I say you interrupt பொறுத்த வரைக்கும் understand the priority of the interrupts, understand, keep in mind the location which is mentioned for the maskable and non-maskable interrupts. Okay, and those two things and ISR in the moon mattu correct anga avoidno, right? Just take a moment to make a note of this. If there is any clarification needed, let us know. Shall we move on to the next one? Silence indicates yes. Thank you, Ritesh. Thank you, Akalya. Okay, as always, Praveen. Yeah. Thank you, Praveen. We'll move on to the next one, right? So having said that, we have completed addressing modes and interrupts. Now we will move on to the next important part in our module 3 is the instruction sets which are available in my 8085 microprocessor. Okay, when I say instruction set, what it means is these are the instruction codes which are used for performing a specific task like addition, subtraction, finding the complement, finding the AND operation. So it is something like a command, or command and instruction are both on the same, right? So the way in which you are going to communicate with your system to make sure that system understands that particular command, so that is what is called as an instruction set is all about, right? And the complete number of instructions which are available in our 8085 are put into either of this classification of these 5 categories. First category is control instruction, second is logical, third is branching, fourth is arithmetic, fifth is data transfer. Okay, so out of this 5 we will see 3 today, and 2 we will keep it reserved for the next class, right? I suppose it is 10:35. So I suppose 3 we can work out today. Okay, so first one, when we see control instructions. Okay, on screen you will find that there is something called opcode, operand, meaning and explanation. Okay, whenever we say microprocessor programming, it should have it should come always with an opcode and an operand. Okay, an operand, which I mean is where either it could be a data or it could be a address. Okay, இப்போ நம்ம அந்த முன்னாடி பார்த்தது தான் இங்க எக்ஸாம்பிள்ஸ் பார்த்தோம்ல இங்க move immediate k, 20. Here MVI stands for the opcode, k, 20 stands for the operand. Okay, so that is what is. So opcode பொறுத்த வரைக்கும் அந்த instruction directly. First one, when you see NOP stands for no operation. That is, this command is executed or used in our programming to give and to make a small delay to it. Okay, so when you use this command, no operations is being performed using this command, but a little bit of execution time is taken to this. In terms, it can be called as a intentional delay which is inserted to the program, right? Moving on to the second one, it is HLT. Halt is the expansion for it, right? So what happens is whenever you write a program and finally you mention this statement HLT. Okay, so what happens is, look at the explanation. The CPU finishes executing the current instruction and stops further execution. Okay, an interrupt or reset is necessary to exit from the halt. Sometimes when we use a program, right? Program பண்ணிட்டே இருப்போம், ஒரு இடத்துல வந்து அந்த இடத்துல we will stop that particular operation. ஒரு arrangement of numbers either in ascending order or descending order. Say for example, that is the one thing that we can take. அந்த ஒரு எக்ஸாம்பிள் எடுத்துக்கிட்டோம்னா ஒரு 50 நம்பர் வந்து நான் அரேஞ்ச் பண்றேன் அப்படின்னா 10 நம்பரா நான் வந்து டிஸ்ப்ளே பண்ணணும் அப்படிங்கும்போது ஒரு 10 அவுட்புட் டிஸ்ப்ளே பண்ணதுக்கு அப்புறம் ஹால்ட்னு ஒரு கமாண்ட் கொடுப்பேன். ஓகே, அப்ப கொடுக்கும்போது என்ன ஆகும்னா the system will wait for me to give an signal to display the next 10. At that point of time, what I can do, I can use my keyboard to press an enter key or something like that. So that will go in as an interrupt signal to my processor and it gives the next 10 data, right? So அதுதான் the halt operation. அப்படி பின்னாடி எதுவுமே இல்லை அப்படின்னா அந்த halt அந்த program அதோட ஸ்டாப் ஆயிடும், right? It could be to stop the program or to have a temporary finish of it. Then it is DI and EI. DI and EI stands for enabling the interrupts. DI stands for disabling the interrupts. EI stands for enabling the interrupts. Okay. The interrupt enable, there will be a flip-flop which is available in all cases. That's why we have studied digital electronics earlier to this microprocessor, right? This flip-flops, interrupt enable will reset this flip-flop, okay? Except the trap, all the interrupts can be disabled, okay? Whereas enabling interrupts, okay, the same thing, the interrupts which you have disabled can be enabled with this case. When you give a disable interrupt command, DI command, your flip-flop is reset. When you enable an interrupt, EI command, your flip-flop is set. Material which flip-flop it is, right? And then as how you have got enabling and disabling of interrupts, you also have something called RIM and SIM. Okay. This RIM stands for read interrupt mask. Okay. Just hold on. Yeah. RIM stands for read interrupt mask. Okay, so here this instruction is used to read the status of the hardware interrupt. Hardware interrupt நம்ம எதெல்லாம் சொன்னோம்? 5.5, 6.5, 7.5, trap and INTR. So அதுல இந்த மூணு 5.5, 6.5 and 7.5 இருக்கக்கூடிய ஹார்ட்வேர் இன்டரப்ட்ல என்ன இருக்கு அப்படிங்கறத பார்த்து by loading that into our A register, okay, and then it defines the condition of the mask bit for the interrupt. Okay, இங்க தான் வந்து என்ன பண்ணுவோம் அப்படின்னா we will use a command like SID அப்படிங்கற ஒரு command யூஸ் பண்ணுவோம். Serial input data, serial data in அப்படிங்கிறது. Okay, so RIM பொறுத்த வரைக்கும் serial input data அப்படிங்கறது யூஸ் பண்ணுவோம். ஏன்? We are going to read an interrupt mask. So serial data is input to the system. Okay. And similarly, when you come to the next one, SIM, set interrupt mask. So under set interrupt mask, this instruction is used to again implement the same hardware interrupts like 7.5, 6.5 and 5.5, right? This will be set by various bits to form mask and generate output data. Inge output data generate agum, anga input data generate achu. When I say output data is generated, instead of SID there, here it will be SOD, serial data out. Okay, so this is what is the difference between SIM and RIM. So all these things are control instructions which are going to say you, again the control instruction still comes back. CMP, compare the registers. Now in the earlier slide you have seen all your operands as none, right? But in this case you will start to find R or M or something like this. R stands for register, M stands for memory, and this is a data which is directly available. Okay, so look at the first that is for control, and this is, let's now move on to logical instruction. Under logical instructions, CMP stands for comparing the register or memory. R stands for register, M stands for memory. So with what you are going to compare is, you are going to compare with the accumulator value. Okay, so look at the explanation. The content of the operands, which could be either a register or memory, or compared with the contents of the accumulator, right? ஒரு செட் ஆஃப் ப்ரோக்ராமிங் போட்டு இதுக்கு இந்த சிஎம்பிங்கிறதுக்கு முன்னாடி ஒரு ஸ்டேட்மெண்ட்ல நீங்க ஒரு ஆப்ரேஷன் பண்ணியிருக்கீங்க, அதனுடைய ரிசல்ட் இருக்கும். அந்த ரிசல்ட்டை கொண்டு போய் அக்யூமுலேட்டர் வேல்யூவோட கம்பேர் பண்ணணும். இந்த கம்பேர் இன்ஸ்ட்ரக்ஷனுக்கு முன்னாடி என்ன ரிசல்ட் இருக்கோ அது வந்து will be compared with the accumulator. Is that clear? Then CPI, compare immediate with the accumulator. Okay, there it is completely been taken care. Here it is a second byte which is அங்க ரெஜிஸ்டர் ஆர் மெமரின்னு இருந்திருக்கும், இங்க வந்து டேட்டா. கம்பேர் இமீடியட் வித், இங்க ஒரு டேட்டா வேல்யூ கொடுத்துருவோம். கம்பேர் இமீடியட் வித் 20 அப்படின்னு ஒரு டேட்டா வேல்யூ கொடுத்துட்டோம்னா அக்யூமுலேட்டர்ல 20 இருக்கா அப்படின்னு பார்க்கும். இருந்தா கம்பேர் அவுட் ரிசல்ட் வந்து செட் ஆகும், இல்லைன்னா ரீசெட்ல ஜீரோல இருக்கும். ஓகே, so this is between a register or a memory. CPI directly compares immediately data with the accumulator. Okay, then it is ANA, logical and register. Again ANI, logical and immediate. எல்லா இடத்துலையுமே and operation, இது வந்து exclusive OR operation, right? எல்லாமே வந்து we will either first do with register or memory, and in the second case we will do with the data directly. Looking at ANA, you will do a logical operation and operation, of course with the data or a register with the accumulator. So what happens here? The contents of the accumulator are logically and with the contents of the register or the memory. The result will be placed in the accumulator only. Accumulator is now overwritten by the end result. Okay, same thing is here, but the comparison will not be between registers. It will be with this data to the value in the accumulator. Result will be in the accumulator. Same like AND operation, an exclusive OR operation is done in this case. XRA with the register memory, XRI immediate with the accumulator, right? So this is one of the logic inputs. Similarly, OR operation, logical OR operation, ORA, ORI, OR operation with accumulator, either with accumulator and register or with memory, store the end result in the memory. Or immediate with the data, store the end result in the memory, sorry, in the accumulator. Okay. Next one is RLC and RRC. This is one of the things that we will be using in our arrangement and programming for ascending and descending order, or moving a bit of data between the word and so. So RLC stands for rotate the accumulator left. RRC stands for rotate the accumulator right. Okay. So here if you see, each binary bit of the accumulator is rotated left by one position when it is RLC command is given. So what it is you start with D0 to D7, right? So whatever the bit value which is at D7 will be now moved to D0. Okay, and of course the carry flag is also moved on, right? Carry flag, how it is, with what value it is modified is with the value which was available at D7. D7 ல இருக்கிறது D0 க்கு வரும்போது அதே D7 ல இருக்க வேல்யூ கேரி ஃபிளாக்லயே வந்து உட்கார்ந்துக்கும். That is with respect to RLC. Whereas in RRC, it is an rotation in the right direction. D0 ல இருக்கக்கூடிய வேல்யூ D7 ல போய் உட்காரும். Same case, your carry register is also modified according to its bit of D0. D0 ல இருக்கு D7 ல போய் உட்காரும்போது D0 ல இருக்க அதே value will be sitting in the carry flag also, right? So is this control and logical instructions clear? Let me know if this control and logical instructions are clear. You don't have to write all these instructions which are available there, right? Of course, this will not be asked as a 16 marks question on the whole. This will be asked as an 8 marks question, asking you to explain any of the 2 or 3 instructions, right? So when you write logical instructions, you write the basic R and XR with A and with I immediate, right? And the control instructions போகும்போது it is quite simpler to you, right? அங்க இருக்கக்கூடிய அந்த ஒரு 6 control instructions தான், right? Default-ஆ வந்து உங்களால NOP அப்படிங்கிற ஆபரேஷன் சொல்ல முடியும். Then disabling an interrupt, enabling an interrupt, reading an interrupt mask, setting an interrupt mask, RIM, SIM, right? And of course HLD. Quite easy to remember, but you will always have to go through this again and again, right? Is that clear? Shall we move on to the next one? Sedu, thank you. Praveen, yes, okay. As usual, somebody from A section and B section. Somebody from A and B. Arunita, thank you, from A section. B section? Pratish. Same guys. Thank you. Yeah, Akalya. Thank you. Clear. Okay. Good. Now, no, the others are making a note of it. So I'm just thinking in that way, right? They are still copying down the instructions in other cases. Right? Okay, let's go ahead. Again, there are, adding to that RLC and RRC, there are few more logical instructions, right? As how you have been doing your rotating the accumulator left and right, this is through carry and that is not through carry. Okay. So there what was happening is D7 ல இருந்தது D0 க்கு வந்துச்சு, டைரக்டா வந்து உட்கார்ந்துச்சு. அதே D7 ல இருந்த வேல்யூ கேரி ஃபிளாக்ல போய் உட்கார்ந்துச்சு. ஓகே, அங்க இந்த கமாண்ட் REAL யூஸ் பண்ணும்போது என்ன ஆகும் அப்படின்னா D7 ல இருக்கக்கூடியது ஃபர்ஸ்ட் கேரி ஃபிளாக்ல உட்காரும். அப்ப கேரி ஃபிளாக்ல என்ன இருந்ததோ அதுதான் வந்து D0 ல வந்து உட்காரும். Okay, so first movement will be from D7 to carry. At that point of time, what was the data which was available in carry will be now moving to D0. So that is your rotate the accumulator through carry, left, REAL. Rotate accumulator right through carry. There it is RLC or RRC. Here RAL or AR. Hope the difference is clear. Through carry and not through carry. Okay. Next instruction is CMA, which is complementing the accumulator. Okay. When you do a complementing of accumulator, no flags will be set. Flags will be set ஆகாது அப்படின்னா எப்ப சொல்லுவோம் அப்படின்னா ஒரு ஃபிளாக் பார்த்தோம், parity flag அப்படின்னு ஒன்று பார்த்துருக்கோம், ஞாபகம் இருக்கும்னு நினைக்கிறேன். End resultல எத்தனை number of ones இருக்கு, if the number of ones is even number then it is even parity, if the number of ones are odd, if it is odd parity அப்படின்னு சொல்லியிருக்கோம். Okay, So accumulator la irukakodiya value la vechi da nama the parity flag set aayirukkum illa reset aayirukkum. When we are going to use this CMA, it is going to complement the accumulator, zeros into ones and ones into zeros. At this point of time, nothing will happen to the flag register. Flag register remains unaffected because of this command, right? It gets affected only because of the results which is coming out of a particular operation only. Is that point clear? Now, moving on to the next one, it is CMC, complement the carry. Again, in the complementing the carry also, there is nothing is going to happen with respect to the flag. Only the complementing of the value which is available in the carry flag is going to happen. Hope I'm able to make the point clear. And then it is another command called STC, set carry. So this is a command which is used to intentionally make your carry flag as logic high. Okay. With that, our logical instructions are over. Now let us move on to the branching instructions. When I say branching instructions like jumping, JMP stands for jump. Jump is with an operand of 16-bit address, okay, and this is an unconditional one, okay. You can represent an address there, JMP 2000. That means the flow of program will now move on to the address of 2000, leaving behind what is available after the instruction, right? So that is an unconditional statement. Okay. So here the program sequence is transferred. Sequence of the program is transferred to the memory address given in the operand. Okay. So examples of this are JC, jump on carry. This is a conditional statement. Here also you had an unconditional statement. Immaterial of what is the result of a zero flag or carry flag or parity flag. When you mention this command JMP and an address, it moves directly to the address. But whereas in this case, this is a conditional jumping statement. JC, jump on carry. When the flag status is equal to 1, when this command is given and an address is here, that point of time, when CY is equal to 1, this moves to this address. Your flow of operation, sequence of operation will be transferred to this address when CY is equal to 1. Similarly, when I use JNC, jump on no carry, that means whenever my carry flag is not equal to 0, that time only the sequence will jump to this address. Again, this is on parity. Jump on positive, jump on minus. Okay. Jump on 0, jump on no 0. Jump on parity even, jump on parity odd. Is the point clear of how this is being done? Conditional and unconditional jumping instructions. Am I making that point clear between jumping and unconditional jumping instructions? Anything which is unconditional, it is directly moving to your particular address. When it is conditional, we means it is dependent on the flag, sign flag or zero flag or parity flag or carry flag. Based on the nature of that flags, the jumping instruction happens. That is conditional jumping. Okay. So, yeah, thank you. Now, let's move on to the next one, right? So there is something called CC. So all these things, upcoming CC, CNC, CP, there we had jumped to the location. Here, it is going to have something calling an operation, right? So when you use the term CC, it calls to a particular subroutine program on a condition like whenever this carry is equal to 1. Okay, look at the explanation part here. The program sequence is transferred to the memory address here given by the before transferring the address of the next instruction after call is pushed to the stack. And it is something like transferring this to this address, and this address you will have a subroutine program. Okay, that subroutine program will happen here. Okay, on the condition of when carry is equal to set or carry is equal to 0, sign positive, sign, minus 0, flag is set, 0 flag is not set, parity is even, parity is odd. As how it is jump, this is call, right? JPO, CPO, JPE, CPE, JNZ, CNZ, JZ, CZ, right? A word J is replaced with C. Okay? Then, whenever you use this terms, call statement, it's how like you do in your programming. Whenever you go to a subroutine program, you should also come to a return program. This return is available at that particular program. When this instruction is given, this moves on to the previous line. Okay. I said, whenever these operations are done, the immediate next instruction of this command will be stored in the stack pointer. Stack. Right? So return command கொடுக்கும்போது என்ன ஆகும் அப்படின்னா அந்த ஸ்டாக்ல என்ன அட்ரஸ் இருந்ததோ அந்த அட்ரஸ்க்கு திரும்ப instruction will come towards. Okay, and return again you have got your conditions. Return on carry is equal to 1, return on no carry, return on positive, return on minus, return on 0, return on non-zero, return on parity is even, return on parity is odd. All this jump, call, return are going to work only based on the flag registers. Carry flag, 0 flag, sign flag, parity flag. Is the difference you are able to understand clearly? Okay. And there is something called PCHL. Okay. PC stands for program counter. HL stands for the H register and L register. We have seen 6 registers, right? B, C, D, E, H and L, right? When you use a word PCHL, what happens is the contents in the H register and L registers are copied to the program counter. Okay, என்னது H registerல இருக்கக்கூடிய வேல்யூ வந்து higher order byte லையும் L registerல இருக்கக்கூடியது வந்து lower order byte லையும் போய் it will sit into it. That is the work of this PCHL. Okay. Then this is an instruction for RST, restart. It's a software interrupts, right? And as already said, there are interrupts. Whenever you give an interrupt, you have an address specified to it, right? RST 0, we have said this, trap 0024, 5.5 2C, 6.534, 7.53C. Similarly, your software interrupts also has a specific address available here. Right? RST stands for reset or restart. Is used in the software instructions in a program to transfer the program execution to any of this value. RST 0, RST 7.5, RST 6.5, something like that. Right? But this, you can use it only for this only. For software interrupts only. Not for the hardware interrupts. Okay. So that is all to do with your branching instructions. So out of the 5, we have seen control, logical and branching, right? So I believe that it's 10:56. So time for us to revamp what we did today with a little recap of what we had taken last class. We moved on to the pin details of 8085. And then we had seen the 5 different addressing modes which are available. Okay, the 5 addressing modes were immediate, register, direct, indirect, and implied. Those were the 5 addressing modes which were available. Okay, then we had seen something on interrupts. In interrupts, we had seen what is an interrupt and what are the different interrupts are available. Interrupts which are available are 5 in numbers. Trap 7.5, 6.5, 5.5 and INTR. Trap has the highest priority and INTR has the least priority. Then the interrupts are classified into 3 different common classifications. Number 1 is vectored and non-vectored. Vector is something which has a known address. Non-vector doesn't have an address. Then maskable and non-maskable. Yes, except for INTR, all the other things are maskable, while INTR is non-maskable. Then we had seen on the classification of software interrupts and hardware interrupts. Those 5 interrupts that we said as INTR, trap, 5.5, 6.5, 7.5 are hardware interrupts. And software interrupts are something like RS0, RST1, RST2, and it goes until RST7. Okay, so those things were with respect to interrupt. Then we came to the instruction set. On instruction set, we had 5 instruction sets, right? 5 instructions, namely control, logical, branching, arithmetic, and data transfer, in which we had seen control instructions, NOP, HLT, data, disable interrupt, enable interrupt, read interrupt, set interrupt. Then on logical, complementing, comparing, AND operation, XOR operation, OR operation, rotating left and right without not through carry. If this is RAR through carry, CMA, CMC for complementing the accumulator and complementing the carry and to set the carry, STC. Then we came to the branching instructions, namely JMP, jumping unconditionally. Then jump on based on the flag natures, JC, JNC, JZ, JP, based on the carry flag. And then we use something calling with respect to the flag nature subroutine programs, right? So that is with respect to this call operations, call on carry, call on no carry, call on positive, and so. Then we had seen on returning, as of whenever you use call, we used to have return also. So return on carry, return on no carry, and so. Then whenever you want to move the value in HL pair to program counter, you use a command PCHL, and then on RST for your software interrupts restarting, right? And its address which are available. So that is all from us on today. And are there any clarifications which is needed? If so, just drop a message in the chat box. And there is no clarifications. We wish you a wonderful Puja holidays. Vijayadashmi, Ayudha Puja. Have a nice festival time with your family members. Enjoy your days with your family, right? Thank you from both of us. Take care. Bye-bye. We'll see you in the next class.